In this video, I'm going to be going through true length as it relates to Year 12 or HSC engineering studies. To start off with, I'm going to explain what the concept of true length is, and then we're going to look at development drawings based on notes, these drawings here. We're going to focus specifically on this first drawing once we understand the concept of true length. So, first of all, Copeland has this text which helps us to identify if a length is a true length. What that means by that is that sometimes in a HSC, in an orthogonal drawing, sometimes the lines that we see, they are misleading in their length. Now, I'm going to summarize. You can read, so I'm going to summarize and say that the first rule says that if the line is shown as a dot, or a point in one view, then it will be a true length in the other view. And then it says here, I'll read this one out. If in one view the line is perpendicular to the viewer, in the other view it is a true length. Now we'll start by just looking at a HSC question that demonstrates the idea of a dot. So the idea is that in this question here, we have a pole, and the top view, we could imagine this pole being viewed by a drone. And in this case, the pole, we could measure that pole as being to scale, and we could say that that would be an accurate representation of the pole because it's a dot in this view. However, lines, the cables 2, 3, and 4, they are not true lengths, and we'll explain more why that is in a second. When we go to this question here, so we have a shape, and it's what we call a truncated pyramid, except we'd call it an inverted truncated pyramid. So a truncated pyramid looks something like this. We take off the tip of the pyramid, and this particular one is upside down. So it's an inverted truncated pyramid. And we might consider this to be like a bowl, right? A really fancy bowl, right? So maybe a centerpiece and a table. And what we're looking at is that we're looking at the opening, and we're looking at the base of the bowl here, and this is the opening of the bowl. And here we're looking at the side of the bowl. Now we can see these two lines. Well, it's the same line, but in the top view and this front view, this line AB looks very different. So the question is, well, which one is the correct length? They can't both be the same length. So if we wanted to make this bowl, how would we know what length that line is? Now, the multiple choice questions, multiple choice options we have is that it could be 10 millimeters, which is what we'd measure here. We'd say that's 10 millimeters. Or it could be 30 millimeters, which is this distance here. But in fact, it's neither of those lengths. In fact, it's the hypotenuse of those two lengths. This represents the horizontal distance, and this represents the vertical distance. And in fact, the true length is a diagonal distance that is not flat to the camera in either view. Now, what does it mean when I say flat to the camera? Well, we have this drawing here of a triangular pyramid, or a tetrahedron. It's got 4 sides, and it's a bit of an odd, unusual shape. So what I've done is I've drawn this shape, but I've drawn it in, I've copied the diagram, and then I've drawn it in, I've just traced it. And what we can see here is we've got our top view and our front view. And when we look at this top view and front view, well, we have this location here. Let's start by looking at it from the side. So if we look at it from the side, if we look at it, imagine it in this box, what we can see is the box maybe isn't all that helpful. We'll maybe get rid of the box for a second. What I'm going to just do is I'm going to move it this way 1000. And then I'll bring it back later. Okay, so if we look at this pyramid, we can see it's a 4-sided shape. And what we're looking at is it's this 4-sided shape, and we can see that there's 4 sides. So first of all, we have what I guess we could call the top view. And when we get the top view, we can see the top view is this one from the top, and then we have, I guess we could call it a left-hand side and the right-hand side, and then we also have another view, which is another side, which is underneath. We can see that there is a back side, right? So there's 4 sides. We have the front, which we can't see anymore. This, we can see the left, we can see a little bit of the right side, and then the back side underneath. Okay, so with that said, we've now got a concept of what our shape is. What we're going to look at is this concept that I talked about, the viewing plane. Now, when we're discussing shapes, where did I move this? 1000. I moved it. This all this thing here. Is that right? Yeah, okay. Move. Oh, I'm looking at this upside down. That's what's going on there. Okay. We upside down, but I'll quickly fix that up. Okay. So what we're looking at now is, if we look at this from the front view here, this is our front view. It says so on the box at the top there. This is our front view. Now I've drawn this pink line as sort of as a post to hold up this shape. We don't need the post, but I needed I needed it in order to be able to draw the shape accurately. I needed some sort of vertical line, so I thought I'd keep that in there. But I suppose we could actually delete that and it would still be what we're actually looking at here. So let's go back and look at it again. We can see that we've got this shape. And then if we look at the top view, well, we can see that it says the word top and it looks exactly like we see here. Now, if we look at it from a slight angle, we can see that we have this object. Now, the thing that's confusing, if we go back to what it looks like in our drawing, we can see that this line here, which appears as a dot, let's call this, sometimes I label these. In this case, I haven't done that. We'll call this the vertical line. This vertical line appears as a dot in the top view. It's effectively not there. There's nothing. It's an infinitesimally small point. And we can measure that and say it's 48. Now, if we look at our diagram, we can measure that distance by going here, clicking here and here, and we can see it's 48.1. Well, we'll just call it 48, right? So I traced it, so it's not perfectly accurate, but 48 is exactly what we measure. Now let's have a look at this this line here along the ground. We've said 47.4, and you can see that I had, on the top view, I had 47, so that's correct as well. Now what's interesting is, let's have a look at these side views. Now if I measured this line here, it says that's 48, and if I measure this one here, we can see it's also 48. So we might think, oh, well, this line here, this bottom chord is 48, but in fact we'll find out that it is not 48. Again, I'm going to delete this now because I don't need this anymore. It's a bit of a pain to draw that, but I think it's done more harm than good. Oh, we'll see. Maybe we'll bring it back. Okay. What we're going to see is that this line is in fact not 48. It's actually 53. And the reason why it's 53 is because it is not parallel. This line is not parallel to either the front view or the top view. Actually, you know what? We will just bring back that box just because. So here we have the front view. And that line, this bottom line here, the 58mm line, is not parallel to the box of our front view. It's not parallel to that. And it's not perpendicular to the top view either. It's not, sorry. This line is not, it's diagonal in every direction. It's not parallel or perpendicular to any of these faces. So I find that really helpful to think about when we're trying to discover which of these shapes are parallel. Now, the question wasn't actually asking anything like that. The question was asking how many lines in this are shown as true lengths. Well, what we can see here is that in this top view, the line is a dot, and then we have the vertical line. And here we have the horizontal line appears as a dot. I'm going to actually come over here because the cursor will show up better here. Here, this dot is the vertical line, that's a true length. And here, this horizontal line is a dot, so that's a true length. So there's two true lengths in this diagram. Let's have a look at some of the other questions. So we have another question here. Actually, we're going to go to this one. This one's a bit easier. So this one here says, how many edges in the views below? Now, it's really important you read these questions really, really carefully, because sometimes not reading the question carefully can mislead. So it's both views. Sometimes it might just be in the front view or the top view. So in this case, it says in both views, how many true lengths are there? So we've got this pyramid. It's, I guess, a pentagonal pyramid. And when we look at this object, let's see what it looks like first. So the pentagonal pyramid looks something like this. And the question is, how many of these views are correct? Now, we can see that when we draw this, that each side of the pentagonal pyramid is in fact 23 degrees. And we can, let's just quickly measure the length of the pentagonal pyramid. The length of the pentagonal pyramid is, we're going to call it 37 degrees. Now that's a bit bad because my tracing is a bit uneven. So what we're looking at here is, we said that the line was 37, but I've measured this here as 35. And the reason for that is because we can see this line here, it's not perfectly, this line here is not perfectly perpendicular to the viewing angle. If I click on the front view, this line here is not perfectly perpendicular. It's actually falling or sloping away from the viewer. Sometimes I use the term like the camera. So the glass of the camera, this line is actually going, it's sloping from the bottom to the top. It's further away at the top than it is at the bottom relative to the camera, or the camera of the viewer, the plane of reference. So when we measure here that this is 35, whereas this line here, now don't fail me now because I did trace this. This should be 37. I got 35. Okay, I was a bit sloppy with my tracing. But this line here is in fact a true length. And why do I know? How do I know that this line here is a true length? This one here is a true length because it's not a dot in this view. So if I was to label this, sometimes I label like, I go 1, 2, 3, 4, 5. 5-0 is a true length. It's not a true length in this view, but it is a true length in this view. 5-0 is true in this view. How do I know this is true? Well, I know it's true because, not because it's a dot, we said dots are true lengths, but because it's perpendicular to the viewing angle on the top view. Because it's perpendicular to the viewing angle from the top view, you're going to send a message? Because it's perpendicular to the viewing angle from the top view, we can then say it's a true length in the front view. Now, what other sides? So we've got that one there is correct. Also, this line here is a flat line. So if they call this, what do we say? This is 5-0. So 5-1 in the top view is a true length. Why? Because it's a perpendicular line on this view. And then this one here, 1, 2, again, we can't see it, but it would be there. So we've got 1, 2, this one here, because it's we can imagine this slope is the face of this pentagonal pyramid is completely flat. It's completely parallel to the top view. And as a result, all of these lines, 1, 2, 3, 4, 5, they're all true lengths. So we can say that there's at least 5 true lengths. Also, this line here is a true length. So that gives us 6 true lengths. Now, there's a way that someone might say, well, this 5-1 is, or let's actually, a better example, 4-1. Sorry, 4-5, this line here, 4-5, I haven't labeled these, which makes it harder. 4-5 is a true length here. It is not a true length here. And that's the case as well. So see how this one here, let's call that 5-1, 1-2, 2-3, and 4-5, and 5-1. They're all true lengths, but they're only true lengths in the top view, right? They're only true. If we got a ruler out, that's true. They're 23 all sides, right? If I dimension these, they're 23 across the board, right? They're all 23. But if I measure it here, I'm going to get 22. And when I measure here, that same dimension, is not 23, right? It's clear that it's not 23. So these sides, 5-1, 1, what do we call this? Yeah, 5-1, 1-2, 2-3, 3-4, and 4-5. They're all true, but only in the top view, right?
Doesn't that break our perpendicular rule?
No, because they're flat on this line here. I like to think of it as they're parallel to the reference plane. Yeah, they're parallel to the top view, which they appear as a perpendicular line.
No, I just needed that they were flat in the bottom.
Yeah, okay. So because they're flat in the bottom, that means that they're... okay, and then I have this line here. This line here in both views, we know that this line here is actually, it's effectively as a line, the top and the bottom are both an equal distance from that front view. When we talked about the front view, if we put this in a box, the face of the front view, this line here is the same distance away from my eyeballs as it is here. It's not slanting back or forward. Whereas this line, on the other hand, it is slanting backwards. Right here, it's further away than it is there. Right? The tip of the pyramid is further away from me than it is at the base of the pyramid. Whereas this line, it's actually not. It's actually the same distance away from my eyeballs the whole way up and down the line. It's the same distance from me here as it is from me here. Yep, okay, so that's this pyramid. So the answer here is all 5, 1, 2, 3, 4, 5, 6 is the answer for that question. Okay, so we're going to move over to this hexagonal pyramid, and we'll do the first thing of look at it from a diagram. And okay, so that's what it looks like. We've got the height of our hexagonal pyramid. We've said the sides are 17 each. Remember that I've traced these, so it makes it a little bit difficult to get totally accurate distances. Now, in this view, it says we have to, how many visible, and it's in big capital letters, how many visible true lengths are in the front view of the hexagonal pyramid. So it really pays you for reading. It says only the front view. We're not counting any of the true lengths in the top view. So these sides here, 1, 2, 3, 4, 5, 6, we're not counting those because they're not in the front view. Now, which views are true? Well, in this case, it says visible. This line here, now they've actually labeled these for us, which makes it so much easier when they've labeled them. Okay, here we can see AF. This is AF here. Is AF a true length in this side? No, because it's not 17 degrees. It is 17 millimeters. Let me measure it and I'll show you that this distance to this distance is only 9. And we know that the true length is 17, right? So it's not that one. Okay, well, what about ED? The same thing. ED, we know that it's not, we can just see it's not the right size. But why? Because it's not, it's sloping away from the viewer, right? Whereas this one here, FE is a true length. It's 17. We can see that it's the same dimension in both. Now, just because it's the same length in both sides, that doesn't make it true. Remember this one here, this pyramid here, we saw that was the same length, and it was still misleading, right? Because it was sloping away the same amount in both views. What we're saying here is just because it's 17, that's not the trick. The trick is that this, we can look at this diagram and we can say this line, which we called EF is the same distance away here from my eyes as it is here. F is the same distance to my eye as E is to my eye. If I was shooting out laser beams like I was sonar, the distance from my eyeballs to EE is the same distance to F. Therefore, we can say that it's parallel to the viewing plane of the camera or of the box. And Copeland would refer to it as perpendicular, right? I can live with that. What he means is perpendicular to the axis of my eyeballs. If you drew a line through the axis of my eyeballs, you could say that that line was perpendicular. I like the idea of viewing planes, but, you know, Copeland's been doing this a lot longer than me, so, you know, I've got to appreciate that he might have a better way of expressing it. Now, the same way that this line, the line AO is the same distance away from me, from my eyeballs, as A is the same distance away as O. And D is the same distance away from O. So that means AO and DO, they're true lengths. And I've measured that as 34 millimeters. And let's demonstrate that when we zoom in here on this thing, what I actually want to do is this one. When I zoom in here, you can see that that is, let's measure it, DI. Okay, so we've got 33.9 or 34, and that is in fact the true length. Now, this is a good way of demonstrating as well. Oops. Sorry. That this line is not a true length, right? And why? How do I know this is not a true length? Dim is what I wanted. Sorry. Here we've got 31. So the length of the pyramid can't be different lengths. I know it looks like they're different lengths. Here it looks like it's 31, whereas we know in actual fact it's 34. And we have to rely on the fact that this line, what was that, EO? EO is not, it is not perpendicular to the viewer relative to Copeland, or it's not parallel to the viewing angle or to the camera angle of the top and front views. And that's how, when we talk about true lengths, what we're talking about in terms of how we can identify what's a true length. Now, what I'm going to talk about now is, now that we've got that concept of true lengths, I'm going to move on to developments. And to talk about developments, the first thing we need to do is we need to understand how we can measure a true length. Now, you can see here I have lots and lots and lots of drawings, and I realize that looks really confusing, but it's not intended to be confusing. It's just so that this video will not be as labored. Now, if you want to watch me do it in real time and you don't want to see as many pictures, that's fine. I recorded another video. Unfortunately, when I was using OBS, I wasn't paying much attention to how much of the screen I was cutting out, so that was on me. Okay, so here we have this shape, and we said earlier, where does this shape come from? It comes from this booklet, right? This booklet. And what are we going to do here? What we're going to do here is we're going to draw a development. In primary school, we call these nets. We're going to draw a development for this shape. We're going to show, and why is this important? Well, back in the days of sheet metal work, or not really a thing in Australia so much anymore, I mean, it still exists, but it's not a big thing, is that sheet metal workers had to be able to produce drawings that would allow, engineers had to produce drawings that a sheet metal worker could manufacture. So that's where we're coming up with these drawings. I guess it's still a good concept, and it helps us to have a better, really accurate understanding of how developments work. So what we've got here is we've got this drawing. I've just, I haven't traced these. I've done these a bit more accurately than tracing. But we've got the shape, and what I wanted you to see first is the object that we're producing. So the object we're producing here is this truncated pyramid. Now, in order to be able to, I'll show you what the end result looks like. The end result that we're going to produce is this red shape. That will be what the HSE should look like. The HSE answer should look like is this shape here. That's what we're producing. Now, why is it only that shape? Well, the reason is there's the metal workers, they're pretty smart, and they don't expect you to have to do the whole thing. They only want you to do one half of the drawing. If you do half of the drawing, that's sufficient, or more than half. That's sufficient for them to be able to draw the rest of it. Now, in this case, we've often been given a line which we call a seam, and that's where the two halves get welded together. That's pretty common that we get a seam. Now, before I get too far started, I'm trying to use some color coding to help us understand what's going on. So here we have this shape, and the red line represents the base. It represents the ground. The orange rectangle, it represents the top of the truncated pyramid, the top face. I could have rendered this, but I actually think it's better without. And what we're looking at here is we can see that we have a yellow line and a green line. In order to be able to calculate the distances, we need to be able to triangulate. And so the triangle is going to, in order to find this point, right, which I have labeled somewhere as 3 or something like that. In order to be able to find that point, what I'm going to need to do is I'm going to need to triangulate this orange line and this yellow line, and those two lines together will be enough to help me find this point. So I'm using a compass, and I'm going to use a compass to find the orange line and the yellow line, and those two lines together will allow me to find this point. And then, as we keep going around the shape, I'm going to have to do the same thing again, but I'm going to use the green line. And because the orange sides are all the same, I'm going to triangulate this point here. This is point 3, and I'm going to triangulate point 3 using those two lines and a compass. And where the two lines intersect is how I'm going to draw my drawing. Like we said, I don't need to draw the rest of the drawing. So let's get started. Okay, so first of all, we've got our initial drawing. It looks like this. And I have labeled the drawing just to make life easier. I don't think the drawing is initially labeled in the reference text. No, so I've labeled that. And I recommend you do that. We can see what are the dimensions they've provided us. They've said that it's 56 wide, 56 high, and 84 millimeters long. We can see there's a seam. And sometimes you might be lucky and they may have actually given you the seam as a true length, right? They might give that distance to you if you're really lucky. If they do that, you can get cracking. But that may or may not be the case. Let's have a look. Okay, so I'm going to be referring just to this drawing because it gets a bit complicated. I'm going to be referring to this drawing when I need to. And let's get back to... I've got this blank drawing. I don't know why I have that. I guess it's just the same thing. Yep, that's what that's there for. Okay. So the first thing I want to calculate is I want to start with the seam. You should always, when you're doing these questions, start with the seam. And I have got a model. It's the same thing. But what we've got here is this. Made the seam this rose color, right? This light pink. And the thing is with this line, that is it a true length? Well, let's have a look. Is from relative to the viewing angle here, we can see that that's moving away from the viewer. But in the front view, we can see that it's actually parallel to the camera in the front view. It's not moving away from us relative to the viewing angle. I guess another way of thinking about it is if I was shooting an arrow, or if this is my eyeballs, we would say that in fact, remember I said relative to the axis of the line of symmetry. Why is this not working? Oh, because I'm pressing down, that's why. Okay, so relative to the axis, this is the axis of symmetry of my eyes. This line 0Z is perpendicular to the axis of my eyes. Now that I've done that, what are we going to look at? We can see there's ways that we can mathematically calculate what's going on. So we have been told the height. I just better check that I haven't made the wrong distance. 56 millimeters high is the height of our. 56 millimeters is how high the thing is, and I can just measure this distance across as being 28 millimeters. And if I measure those two distances, the diagonal it's 56 high and it's 28 in the horizontal axis, and the hypotenuse can be calculated at 62.6. If you've got the calculator out, I'm pretty confident that's going to be correct. Now we can just measure that line, that rose-colored line, ourselves. We're just going to go DI and measure DI. And we can see 62.6 is exactly what we had. So we got the same answer. Now that line, the seam, is pretty easy. So we can start by just drawing. I'm going to draw this a third time, right? We can just start by drawing. You can see here I've drawn this line as 62.6 is the seam, right? So if I just go here and I just draw 62.6, I've got my seam. Now, the next thing we're going to do, I could actually make it the rose color. Okay, I've got my seam. The next thing we can look at is, so see all these diagonals. These diagonals are not true length. If we were talking about Copeland, so we mentioned that from my eye, this is the viewing axis of my eyeballs, right? The axis, line of symmetry between my eyeballs. You can see that this line is not perpendicular to that axis. Or we could say that this line is not, this line is closer to the viewer here and further away from the viewer here. So therefore it's not perpendicular, it's not parallel to the viewing angle. So what we can do here is we can do the same concept, right? We can measure the horizontal distance. We can see that the distance from, I guess, the flat plane of the Earth is 31.3 millimeters, and the height is unchanged. In all this question 1, it's a lot easier than some of the other questions because all of our heights are always going to be, the vertical distance is always going to be 56 millimeters. And that makes our life easier. That's not always the case, and other examples are going to be more difficult. But so we can see these purple lines, all of these corners, they are 31.3 in the horizontal direction, and they have we said all of our vertical heights are 56. So that means if we do the hypotenuse from that, if we use the Pythagoras theorem, we'll get 42.6, and let's just measure that when we see that line, we can see that this purple line here is in fact DI 64.15, which rounds up to 64.2. Beautiful. Okay, we're not too worried about that. And I'll tell you why. That one actually doesn't really matter. Right, what we're going to do instead is we're going to go up here, and we're just going to say, well, what lines of this diagram are true lengths? Well, we said before that all of the orange lines are true lengths. We're okay with that concept, right? When we look at them, that surface, that truncated face, is in fact parallel with the with the top view. It's not slanting one way, further or closer to the viewer. And the base of the pyramid, right, which I'm calling the red face, is also perfectly parallel to the top view. So all of those red dimensions and all of those orange dimensions, they're true lengths. So we don't need to worry about those. We can just take those as given. Now remember we said that we need to triangulate. And to triangulate, we need to triangulate this yellow line, and we're going to need to later triangulate the green line. Now, the yellow line is actually pretty close to a true length. It doesn't look like it necessarily, but it's not that far off. So the thing is, from the top view, we can say, well, that line, point A, is further away from the viewer than point 2. Point 2 is closer to us. It's closer to the top view, the camera of the top view. So that means it's not a true length. And if we said, well, what is the horizontal distance? The horizontal distance is 57.7. And what is the vertical distance? Well, the vertical distance for all of our questions is going to be 56. We don't need to look at that all the time, but it is in fact 56. If we use Pythagoras' theorem, we get 80.4. Let's just see if that's correct. So I've drawn a model here of the yellow line. And the yellow line, if we, I've just used the same values. I think I decided to change the colors later. I'm not going to change it now. You just have to accept that those are the values. DI goes from here to here, and we get 80.42, which is exactly what I had before. Okay, so that's one way of doing it, but and that would be fine if you wanted to show, if you didn't know what else to do. That is a way of approaching these questions. You just use the calculator, you get the calculator out, you do the Pythagoras theorem, boom, you have a great time. But there is another way we can do this graphically, and this is the way that 90% of people will answer this question if they approach it correctly. What we can do is we can get a compass out, and we can say, well, we knew that this line here was 50.7. And why have I used the pink line? Well, I've used the pink line to say, well, that's the distance from the orange to the red. Now, pink isn't really between orange and red, but I thought it was close enough that I would say this pink line is the distance from the orange line to the red line, from the top, the truncated top surface of the pyramid to the bottom red surface of the pyramid. And we've said that's 57, and I've shown that in the pink line. Now what I can do is I can just rotate. You can see here that I've rotated. Originally it was going from 2 to A, and I've just swung that line down by using a compass. I've rotated it until it's perpendicular, until it's horizontal in this particular case. And then what I've done is, you can see this red line. This red line says, well, that was at the bottom of the drawing. And because it was at the bottom of the drawing, I'm going to continue that line down until I get to the bottom of my front view. And you can see that's the bottom of my front view. We're saying I'm extending this. Point A is at the bottom. It's on the red face. And I've swung it around. And then I'm tracking that line down until I get to the bottom of my drawing here. And when I get to the bottom of my drawing, it's still on the red face. And I've just extended that line. And we can see that that line is now slightly longer than it was originally. So if we were just to measure the line off the drawing without it being a true length, it would be 79, right? But what we actually want it to be is 80.4. And we can see that small difference. Now, what this means is, if you made a small error, sometimes it won't even be perceptible to a marker, but you're working out as how the marker can see what you're trying to do. Now, the yellow line was pretty close, right? It was a very small difference, and it was pretty close. So what we're going to look at here is some of the times where it's much further out. So here we have this green line. Now we talked before about triangulating the green line. I'll just show you where that line is in case we forgot. So the green line is this, that's actually around the back of the diagram. And in order to be able to find this location, we're going to have to triangulate this. We need this green line to triangulate. And here we can see again, we're finding the hypotenuse of this diagonal line. And in order to find that, what are we going to take? We're going to get, okay. We're going to use this same method. We're not going to use Pythagoras' theorem this time. What we're going to do is we're going to say we have B3. B3 is our line. And what I'm going to do is I'm going to swing that line across using a compass. I just set my compass to the distance of B3, which is 50.8 millimeters. I set my compass to that distance. And then I rotate the line, right, or I produce an arc until that arc is parallel to the front view, or in this case, parallel to the camera of the top view, perpendicular to the front view, or until it's just horizontal is another way of thinking about that. And when I've done that, I've produced this line down here, and now remember that because this line is touching 3 is touching the top view. Can you see how 3 is touching the orange face? The orange face is the top truncated face, the small square. Because 3 is touching the top, when I go to horizontal, I've used the orange line to represent that it's in the top location. And what I'm doing now is I'm measuring from B to my new and more accurate value for 3. Now it just means that I've moved that location. It's where 3 would be if I've rotated the whole drawing to be perpendicular with me. Yeah, perpendicular to the viewing axis of my eyeballs. And we can see that when we do that, we get a number of 75.4 millimeters. That is very different to the original value of 62. It's 10% longer. It's a noticeable difference in the length of that line. Okay, so now we've got these lines. I'm just going to show you an alternative method of producing those lines. What you can do is you can draw up so I measured those distances we talked about before earlier. We talked about, so the distance to the purple lines we said was 31.3. And we can see that's distance here is 31.3. We said that green was 50.5. And let me show you that distance here was 50.5. And finally, the yellow line was 50.7. And here we can see that's 50.7. Now, this is a very clean way of doing your lines. And this is typically what you'll see in HSC answers. What they can say is, now, what is the distance between all of these lines? All of these lines all are the same distance. They're all measured they're all 56 millimeters from the top of the line to the bottom of the line. That is not always the case. I can't stress that enough, that is not always the case. But in this case, because the orange face and the red face, they're parallel to each other, it's all of the values are going to be the same height. And because they're the same height, we could just use Pythagoras' theorem to calculate our angles. Or instead, what we can do is we can just measure and we can just set our compass, because we're going to draw a lot of arcs. Okay, so now that we've got our distances, let's get started. The first thing we've done is we've calculated the distance of the seam. We said that the seam was a true length, right? We said along with the red values and the orange values all being true lengths, we said that this value was a true length. Now what we're going to do is the seam is actually very easy to draw. Why is the seam so easy to draw? Well, if we look at this object from here, we can see that, in fact, the seam is 90 degrees. Yeah, this seam is 90 degrees. And often that's the case. Often in HSC questions, not always, but often the seam is given as being 90 degrees. And when that's the case, what we can do, if it's perpendicular, is we can just say, well, we can measure straight away. We know that this yellow and red values, they're true lengths. So I can just draw them out as 14 and 28. Now you might remember me saying earlier that we don't actually need to calculate the purple true length. And the reason for that, we're very lucky because it's the seam is perpendicular. We have 3 of the 4 sides of our quadrilateral. And when we have 3 of the 4 sides of the quadrilateral, it's not necessary for us to calculate this purple line again. It is a purple line, but we said it was 64, and let's have a look over here. What is our distance? 64.2 is exactly 64.2, and we are going to set it to purple, but the fact is we didn't need to calculate the true length for any of these purple sides. We could just measure it straight off. But we're here and we've done that. Okay, now the next thing we're going to say is that we know that all of the orange faces from here on are 28 millimeters around the top. So what we're trying to find is location 2. Now to find location 2, as we saw when we first looked at our triangulation, to find location 2, we're going to use a yellow line and an orange line. The yellow line and the orange line. Now we need the true length of the yellow line. The true length of the yellow line is 80.4. So what we're going to do is we're going to draw an arc with our compass. We draw an arc that is starting, we're actually measuring the center point, and we said it was 80.4. 80.4, and we're going to say it's somewhere in here. Now I'm going to color this line here as red. The reason why, even though it's a yellow line, actually no, it's not. We're going to keep going. It is yellow line. Yep. Yellow line. Now it's really important that when you draw these lines, you just make really careful that we've measured from the right location. But so we've measured, the yellow line is in fact called 2A. We're measuring from A and we're trying to find 2. So I'm not going to label it this time because we can already see it there. And then we've got the orange line, which is 1, 2. It's the line that goes from point 1 to point 2. Point 1 to point 2. We said they're all 28 millimeters. So what we can do is we can now we draw an arc, and the size of our arc is going to be 28 millimeters. 28 millimeters, and we're going to go from here to here, and it's an orange line. Now the intersection of those points is 2. We have the intersection of 1, 2 and 2A is 2. So we've now found 2. That's our starting point for our diagram. Now that we have 2, we can solidify this line in actually. Right, so we have 2. We've calculated 2. What we're going to do now is we're going to find B. And we're going to find B by using 2B, which we already measured. We said that 2B in all of our cases was 60-something. 64.2. Or we could measure off this line. And that's why we have that line, is we just set our compass to, what was it, 64.2. So setting my arc, I'm setting my center, 64.2, 64.2, and my line should be somewhere in there. Now that's a purple line. That distance there is purple. You obviously won't use colors, but we've now identified, oh, now it has nothing to do with this yellow line. That's on me. And sometimes it's easy to get confused that you think, oh, well, it's this yellow line. No, that's why you want to label your diagram, label your lines. It's very easy to get confused. Now what we need to find is AB. So AB is a true length that was given to us in the diagram. We said that AB was 84 millimeters. So let's get our line. We're going to draw, it's going to be a red line. And we're going to say 84 millimeters. So we want an arc from the center is 84. And there we go. So we've now found point B. And again, we can now, this time we can actually draw in 2 lines. So we've had B. The next thing we're going to do is we can either find 3 or C. I don't care which one. Well, actually, no, we have to find this one. We have to find B because we said that we were going to triangulate using a green line. Now, we could have triangulated a different way. We could have triangulated going the opposite way. And as a matter of fact, this triangulation would have been exactly the same because it's symmetrical. It wouldn't matter. But we've calculated this line here, green. We said the green was 3B. And if we measure our line 3B, we can see it's 74.5. So what we're going to do is we're going to measure from B to 3. And so we're going to set an arc from the center is 74.5. 74.5. And it's going to be somewhere up there. It doesn't look quite big enough. Let me just set it again. Arc center from here, 74.5. Yeah, it's the same. Okay. And then I'm going to set we said always the orange line. So the distance from 2 to 3 is the same as 1 to 2 is 28. So we're going to draw, I really should have done that as a color. And now I'm going to set orange and arc center from here. We're going to go 28. And that's our line. And that gives us location of 0.3. We could do that as orange. Well, I'm setting it as white just to show that it is in fact an orange line, but I just wanted to show it's a line that we've joined, like a dot to dot. Okay, lastly we're going to find point C. So we can find point C using our purple lines. We said our purple lines were 64.2, I'm pretty sure. So let's set that as, I'll go back to purple. Line is 64.2, so arc center 64.2, and then we have our red line, and I can't remember this dimension, it was 56. So we're going to set this one, this is a red line. So arc center, was it 56? I think so. Oh, now I missed it a little bit. Okay, and then we're going to just patch those in. Now, this particular time round, I am actually going to color all those lines, right? Because this is an orange line, this is an orange line, and these are red, and this is red. This is red, and this is orange, and this is orange. Oh no, they're not, they're purple. Okay, that is the one half of our drawing, and we can see that it matches our other drawings that we have here. So that's how we do development 1. I've kind of gone, it's a bit of an unusual way of approaching it. Maybe in the subsequent videos I explain this method a little bit more. I try to avoid that because I wanted to have everything kind of go smoothly by having everything already done. But the idea is it's exactly the same dimensions as these triangles. It's just that I've just drawn all these triangles that I've drawn here. I've just drawn them all at once. So we can see here we have this triangle 1, 2, 3. Here we have 1, 2, and 3. We have the exact same triangles, they're just superimposed over each other. And where we've calculated these distances, or how we've determined these distances, this 31.3, we can see we just determined that distance, that 31.3 was here, 31.3, we just measured the value from the top view. So we could think of all of these purple dimensions as being the top view, which is exactly why they're in purple here, there was that magenta color. It's just the value, the measurement on the top view. Now, it's just pointing out here the yellow value, right, and the value of that distance for the green line is here. So just to make that really clear, that's how we get that value. We just measured it directly off. And you can use this method, the method of rotating it with a compass. That's fine. That's how I did it in high school. But typically in HSE answers, they will show something that looks a lot closer to this. And the subsequent drawings should make this clearer still.